Good morning. Today we will be doing additional problems on convolution integral. This is lecture number 7. Convolute x1 of t equals e to the power minus alpha t into u of t, and x2 of t is equal to e to the power minus beta t into u of t. This is a very important problem, and this problem is asked very often in the examination. So we do the solution now. Let y of t be equal to x1 of t convoluted with x2 of t. This is by definition integral from minus infinity to plus infinity x1 of tau into x2 of t minus tau d tau. This I will call as equation 1. The next step in the analysis is to sketch the functions x1 of tau and x2 of t minus tau. We know that x1 of t equals e to the power minus alpha t into u of t. This implies x1 of tau equals e to the power minus alpha tau into u of tau. U of tau is either 1 or 0. So e to the power minus alpha tau is multiplied by 1 for tau greater than 0. E to the power minus alpha tau is multiplied by 0 when tau is less than 0. Now I am going to sketch x1 of tau. I am going to sketch now x1 of tau. X-axis is tau. Okay. Y-axis is x1 of tau. At tau equal to 0, what is the value of this exponential? It is 1. For tau greater than 0, we get an exponential signal that decays with respect to time. Equation of this curve is e to the power minus alpha tau. For tau less than 0, it is 0. This is how x1 of tau is sketched. Next, I have to sketch x2 of t minus tau. Also we have x2 of t equals e to the power minus beta t into u of t. This implies x2 of t minus tau equals e to the power minus beta t minus tau into u of t minus tau. Again, u of t minus tau is either 1 or 0. So this is nothing but e to the power minus beta into t minus tau into 1 for t minus tau greater than 0 or t greater than tau or tau less than t. E to the power minus beta into t minus tau is multiplied by 0, gives the result equal to 0 for t minus tau less than 0 or tau greater than t. Using this, I am going to sketch now x2 of t minus tau. X-axis is tau, y-axis is x2 of t minus tau. Please note that x-axis is always tau. The arrow here, the y-axis is represented implicitly. Therefore, I have put an arrow on the right side and I have written x2 of t minus tau. Now, the critical point here is t. For tau less than t, this is the expression. So I am going to write tau less than t means the exponential curve will go leftwards like this. When tau equals t, you get e to the power 0, which is 1. Equation of this curve is e to the power minus beta t minus tau. For tau greater than t, it is 0. Now I know what is x1 of tau, I know what is x2 of t minus tau. As I have told earlier, this figure has to be slided against this figure to create overlap for different values of t. This is the objective. Always the figure that will be moving, keep it on left side, and the figure which is stationary, which is immobile, keep it on the right side. Now I consider various cases. This I call figure number 1, this I call figure number 2. Obviously, when t is less than 0, these two figures do not overlap. Therefore, x1 of tau into x2 of t minus tau is 0. I am going to write that for t less than 0, x1 of tau and x2 of t minus tau do not overlap. Do not overlap. Hence, from equation 1, we find that y of t equals 0 because there is no overlap. X1 of tau into x2 of t minus tau equal to 0. Next, I will consider the case. T greater than 0. Next, I will consider the case t greater than 0. T greater than 0. So I will draw the figures again showing overlap. X-axis is tau. This is the sketch of x1 of tau equal to e to the power minus alpha tau. At tau equal to 0, the value is 1. This figure I will show dotted. This is t dotted. This is the sketch of x2 of t minus tau equal to e to the power minus beta into t minus tau. The overlap is between 0 and t. By overlap, what I mean is both the figures are present simultaneously. This is the overlap. For t greater than 0, we find that x1 of tau and x2 of t minus tau overlap for tau varying from 0 to t. This overlapping region is very important because it decides the limits of integration. Therefore, equation 1 gives y of t equals integration 0 to t. Minus infinity to plus infinity has become 0 to t. In the overlapping region, what is the expression for x1 of tau? It is e to the power minus alpha tau. Also in the overlapping region, what is the expression for the dotted curve? E to the power minus beta into t minus tau. Integration is with respect to tau. Therefore, e to the power minus beta t you take out. Integral 0 to t. You get e to the power minus alpha minus beta tau d tau. This has to be integrated. This has to be integrated now. This implies y of t equals e to the power minus beta t integration from 0 to t. Integration is okay. I do the integration. Integrate this exponential. So you get e to the power minus alpha minus beta into tau divided by minus of alpha minus beta. Between the limits is for tau from 0 to t. Now let us put the limits. E to the power minus beta t into, put the upper limit. Since there is a minus sign here, first I will put the lower limit. If you put the lower limit, e to the power 0 is 1. You get alpha minus beta out. If you put lower limit, you get 1. If you put upper limit, you get e to the power minus of alpha minus beta into t. This is for t greater than 0. Summarizing, see y of t equals, please watch, e to the power minus beta t divided by alpha minus beta into 1 minus e to the power minus alpha minus beta into t. This is for t greater than 0, 0 for t less than 0. The correctness of this answer we can verify in this manner. See, this implies when you put tau equal to 0, what is y of t? Y of t, what is y of 0? You put t equal to 0. So what you get? You get e to the power minus 0 divided by alpha minus beta into 1 minus 1. The result is 0. In this expression also you put t equal to 0. So what is y of 0? Y of 0, 0. So both the expressions give identical values at t equal to 0. Therefore our answer is correct. This is the way we have to cross check our answers. Next problem. Convolute x1 of t and x2 of t shown in the figures. This is the sketch of x1 of t. x1 of t and x2 of t in fact are identical. x1 of t, x2 of t. This is the rectangular pulse of unit amplitude, starts at 0, ends at 1. This is x2 of t. x2 of t. Now, solution. Let y of t equals x1 of t convoluted with x2 of t. This is by definition equals integral minus infinity to plus infinity x1 of tau into x2 of t minus tau d tau. As I said earlier, the next step is to sketch the functions x1 of tau and x2 of t minus tau. x1 of tau is very simple to sketch. Only thing is you have to replace t by tau. So again it's a rectangular pulse. Of unit amplitude that starts at 0, ends at 1. Y-axis is x1 of tau. Sketching x2 of t minus t is slightly tricky. Right? Please watch now. We know that x2 of t equals 1 for t taking values from 0 to 1. 0 otherwise. Now I replace t by t minus tau. This implies x2 of t minus tau equals 1. Replace this t by t minus tau between 0 and 1. Now, or this is same as take this t to the other side. So you get minus t less than minus tau. Take t to the other side less than 1 minus t. Multiply throughout by minus 1. So this becomes t greater than tau, tau greater than t minus 1. When you multiply an expression by minus 1 having inequalities, the inequalities reverse. This is same as tau lying between t minus 1 and t. 0, 0 otherwise. What this expression means, x2 of t minus tau is 1 for tau varying from t minus 1 to t. I am going to make a sketch of that. X-axis is tau. I will put a rectangular pulse. The pulse is of unit amplitude. The pulse starts at t minus 1 and ends at t. Y-axis is x2 of t minus tau. So what I mean is when you replace t by t minus tau, the width of the pulse still remains 1 second only, it doesn't change. So for sketching x2 of t, what you have to do is first write the expression for x2 of t from this figure, then replace t by t minus tau, and you get x2 of t minus tau is equal to 1 for tau varying from t minus 1 to t, 0 otherwise. Next what we have to do, we have to slide this figure against this figure. and create overlap. First case, for t less than 0. For t less than 0, for example, if let us say t is minus 1, definitely these two figures do not overlap. For t less than 0, x1 of tau and x2 of t minus tau do not overlap. Do not overlap. Hence, x1 of tau into x2 of t minus tau equal to 0. If you make use of this aspect in equation 1, we get y of t is equal to 0. We get y of t equal to 0. Y of t equal to 0. Next, what I do is second case. First I will sketch the figure. X-axis is tau. First I will sketch x1 of tau. Please watch. This is x1 of tau. Amplitude is 1. This pulse I will push against this pulse. The dotted pulse represents x2 of t minus tau. This starts at t minus 1, ends at t. If you see these two figures, this is the overlap. This is the overlap. Overlap decides the limits of integration. So from this figure, now I am going to write a comment over here for t minus 1 less than 0. See, t minus 1 less than 0 and t greater than 0, or t greater than 0 less than 1. We get from equation 1 y of t equals, please watch, y of t equals, limits become what? 0 to t. How do we get these limits? Nothing but the overlapping region, 0 to t. In the overlapping region, what is x1 of tau? It is 1. What is x2 of t minus tau? It is 1 d tau. If you integrate, you get tau between 0 and t. Therefore, you get the expression t. I'll note down these answers for my reference over here. Y of t equals, earlier case 1, it was 0 for t less than 0. This is t for t greater than 0, less than 1. Please note here, lower limit over here is nothing but the upper limit in this case. For the next case, what is the lower limit? 1. You can see that. First I will put the sketch, then I will write the limits for t. X-axis is tau. The solid line figure represents x1 of tau. This is x1 of tau. Now this could be the scenario. The dotted figure stands for x2 of t minus tau. Where does it start? It starts at t minus 1 and ends at t. This is 0, this is 1. Now where is the overlap? Overlap is between t minus 1 and 1. I am going to write the limits for t. Now put the condition. See, t minus 1 is what? How do you put the condition? T minus 1 less than 1. T minus 1 less than 1 and t greater than 1. I am going to write here for t minus 1 less than 1 and t greater than 1, or t greater than 1 less than 2. Equation 1 gives, I had told you, this is the upper limit 1. For the next case, that will be the lower limit. That is very important. Gives y of t equals limits of integration t minus 1 to 1. What is x1 of tau in this overlapping region? It is 1. What is x2 of t minus tau in the overlapping region? 1 d tau. If you integrate this, you get tau between the limits t minus 1 and 1. Put the limits 1 minus of t minus 1. So you get what? You get 2 minus t. I'll write this answer over here. 2 minus t for t more than 1 less than 2. Last case. If you push this dotted figure further, there will be no overlap. I am going to demonstrate that here. Please watch case 4. X-axis is tau. The solid figure denotes x1 of tau. It starts at 0, ends at 1. This is x1 of tau. This is x2 of t minus tau, dotted figure. Dotted figure stands for x2 of t minus tau. Where does dotted figure start? It starts at t minus 1 and ends at t. When t minus 1 is more than 1 or t greater than 2, again there is no overlap. Therefore, y of t is 0. I am going to write now. For t minus 1 greater than 1 or t greater than 2, we find that x1 of tau and x2 of t minus tau do not overlap. What do you mean by saying do not overlap? This product is 0. Hence y of t equals 0. Y of t equals 0 for t greater than 2. So this is the complete expression for y of t. Now let us verify the expression that we have got is right or wrong. Again, I'll write down that expression over here. Y of t equals 0 for t less than 0. T for t between 0 and 1. 2 minus t for t between 1 and 2. 0 for t greater than 2. Let us check the end points. You put here t equal to 0. So y of 0 equal to 0. If you put here t equal to 0, this also gives 0 value. If you put t equal to 1, what you get? Y of 1 equal to 1. In this expression, put t equal to 1. So what you get? Y of 1 is equal to 1. In this expression, put t equal to 2. You get y of 2 equal to 0. In this expression, if you put t equal to 2, it is 0 only. Y of 2 equal to 0. So these two values are same. These two values are same. These two values are same. Therefore, answer is correct. Now I'll sketch y of t. I'll sketch y of t. Please watch. X-axis is t. Y-axis is y of t. For t less than 0, y of t is 0. For t between 0 and 1, y of t is t. It's an equation of a straight line. This is the equation of a straight line. Like y equal to mx. M is what? 1. X is what? T. Equation of the straight line is t. When t equal to 0, it is 0. When t equal to 1, what is the value? At t equal to 1, the value is 1. For t between 1 and 2, for t between 1 and 2, again it's a straight line. Equation of the straight line is 2 minus t. For t greater than 2, it is 0. So what is important is, when you convolute two rectangular pulses of same amplitude and same width, the resultant is a triangular pulse. What is the width of this pulse? 2 seconds. How did you get 2 seconds? There is a logic for it. The logic, or rather there is a concept. Note, T1 equals width of x1 of t. Width of x1 of t is 1 second. T2 is equal to width of x2 of t. Again it is 1 second. T, let us say TO equals T1 plus T2 is equal to 2 seconds equals width of y of t. Width of y of t. What is important is T1 plus T2 is 2. Therefore, the width of y of t is 2. That also says you are in the right direction. This is how we have to convolute two pulses having same width. And both the pulses are of finite duration. So I have taught you how to convolute pulses having infinite durations, how to convolute pulses having finite duration, so on and so forth. Next problem.